Hi everyone, let's take a look at number 3a on page 178. Find the critical points for each function. Use the first derivative test to determine whether the critical point is the local maximum or local minimum or neither. Step 1. To find the critical point, you have to find the derivative and you set it to 0. So in this case, y is going to be x to the 4 minus 8x squared. When you find y prime, this will give you 4x cubed minus 16 times x. To find x, you have to factor. The first step is there's a common factor of 4x, which you can bring to the front. In the brackets, it's going to be x squared minus 4. If you factor again, notice x squared minus 4 is the difference of squares. So it's going to give you x minus 2 times x plus 2. Which means when you solve for x, there are 3 possible x values, which are the x values for the critical point: 0, plus and minus 2. Again, really important you form the habit of finding the points and not just the x value. And all you have to do is plug in these numbers back to the original function. For example, when you plug in x to be 0, that's going to be 0 to the 4 minus 8 times 0 to the power of 2. That's going to give you 0. Likewise, if you plug in 2 back to the function, this is going to be 2 to the 4 minus 8 times 2 squared. That's 16 minus 32, or negative 16. Now, if you look at the last case, negative 2, you're still going to give you the same y value because x to the 4 and x to the 2 implies this function is going to be even. And an even function is going to be reflected with respect to the y-axis, which means you're going to get the same y value. Now, in order to find out if they're max or min, you have to figure out the increasing and decreasing by drawing a number line. And again, you want to put them in sequence, starting with negative 2, 0, and 2. Now, the slower method, of course, is you plug in these numbers. For example, when it's less than negative 2, when it's in between negative 2 and 0, when it's in between 0 and 2, when it's greater than 2. And there's nothing wrong with that. This works perfectly fine. You can still plug it back to y prime, which would be 4x times x minus 2 times x plus 2. So for example, if you plug in negative 3, 4 times negative 3 is going to be negative 12. Likewise, negative 3 minus 2 is going to be negative 5. And again, negative 3 plus 2 is negative 1. Negative times negative, that's going to be negative. Now, you can continue this, and you should still get the same answer, but a slightly faster approach is to recognize that this y prime, if we put it in standard form, is 4 times x cubed plus a bunch of other terms. And the fact that 4 is positive and x to the power 3 is odd, you can tell by inspection it's going to be positive odd. And because the exponents are going to be odd, it's going to cut right through. So positive odd means the ant behavior is going to go from quadrant number 3 to quadrant number 1. Since it's going to cut right through, you can tell this is decreasing, increasing, decreasing, increasing. And again, if you go through the slower method, you will get the same final answers. So if you want, you can write this down first, and then we'll get to the max and min. So therefore, the interval of increase and the interval of decrease are, it's going to increase when x is in between negative 2 and 0, or when it's greater than 2. Interval of decrease just means when it's less than negative 2, or when it's in between 0 and 2, just like that. Now, the most important part is it a maximum? Is it a minimum? Is it neither? How do we know? So if you go through the first derivative test, all you're doing is this. The fact that the function is decreasing right here, then it continues to increase. This point must be a minimum. So there, right, you can say that, therefore, the minimum is going to be located at negative 2, negative 16. Now, on the other hand, if you look at the next part, it is increasing, and now it's decreasing. And if it's increasing, then it continues to decrease. This really means, and maybe extend this a little bit more, that there is a maximum located at 0, 0. Last but not least, the fact that it decreases and it continues to increase, this point goes back to here, which means there's another minimum, which equals to 2, negative 16. So that's the first derivative test. Now, let's give you a bonus step. Let's make sure you really, really get this. How do we know we're doing it right? All you have to do is double check. And the best way to double check is to draw a diagram. So again, if I kind of go back and write down everything that I have calculated, this is roughly what the graph looks like. And again, it's not a perfect scale, but it's good enough in terms of what you're looking for. So let's say this is negative 2 and 2, and let's say this is negative 16. See, you found 3 critical points, and they are located at negative 2, negative 16, 2, negative 16, and of course 0, 0. And of course we haven't talked about concavity yet, but I'm giving you, roughly speaking, when you graph this, it's first decreasing, then it's increasing, then it's decreasing, and it's increasing. And again, I haven't done concavity, I haven't combined the whole graphing technique with you, but roughly speaking, that's what the graph looks like. And if you go back, there should be an alignment with everything that you wrote down. So for example, that is the minimum. Negative 2, negative 16. 2, negative 16, that's the second minimum. 0, 0 is the maximum. So this is how you do number 3A on page 178. I hope this makes sense.